Hello, everyone, and welcome to the 8th Agda problem-solving session of the HoTTEST Summer School. So today we're going to be talking about HComp and transport. But first, I want to ask, are there any questions that anyone might have about last lecture? So there are some things from last lecture that I think are worth reviewing, so I'll go over them. So we have a primitive operation transp. And for example, we can define transport in terms of it. It's already defined, so I'll just say this. Now, what's the type signature of transport? Well, given sort of a, let's say, line of types, rather, then, and let's call this A. Then what happens is that, this should be an explicit argument. Given a point of A of I naughts, you get a point of A of I 1. And the way that this is defined is in terms of transp. So transp also takes a line of types, but it also takes this parameter varphi, which we're going to just set to I naughts. Now, this parameter is useful, and we're going to see that. So what's there's a difference between a path is always going to be an equality between two things. In Cubical, that's just our name for an equality. There's actually a difference between the type of lines in some type, not necessarily in the universe in any type, and of equalities between their endpoints. And you can sort of implicitly coerce between the two of them by eta expanding, writing lambda I to A of I. That will type as either being a line or a path, depending on what's necessary of it. Does that make sense? So a line, for example, does not enforce the definitional constraints that its boundary points have to be specific values, as an equality does. Right. Now, so the question is, well, what is this varphi parameter? Where is that useful? Well, for example, we can do something like transport ruffle. And I'm also going to define a prime version of this. So here, given it's not exactly a line of types, it's just a single type, which we may as well make implicit because it can be inferred from the latter parameter. And given a point x and a, we can claim that transport in the constants family, in the constant line of x, is the same as just returning x propositionally, not definitionally. And in order to prove this, this is where this I naught parameter comes in. So I probably need A for this. Sure. Transport prime. And what I'm going to do is I'm going to use this transp operation. And I'm going to say, well, let's just consider transporting across the constant type family. We can put an underscore here. That might be more evocative. And we're going to transport with some varphi. And we're going to transport x. Now, if varphi is I naughts, then we're happy because that normalizes to just the left endpoint, transport prime in the constant family of x. If varphi is I1, then this transport is constant definitionally, and that just goes to x. So it looks like if we want to define a path here, what we do is we abstract over an interval variable and put that interval variable as the varphi arguments. And that provides a path connecting these two. In a slightly more interesting example that involves connections, we can also do something like transport. What do I want to do? Oh, transport fill, right. So we have that. Aha, yes. So what happens if X we can think of basically as living in the fiber over A of I naught. So let's say X lives here. Then what happens is sort of we go over the fiber of A of I up until we reach the fiber A of I1. And here the results is going to be transport. A of X, right? Now the question is, can I create a dependent path living over the fibers A of I connecting X to transport AX? And the answer is yes. So given a line of types, then given a point X in A of I naught, what I want to do is I want to construct a dependent path, so a path P, living over A, which I can just put, I don't have to A to expand since it's already a line of types, connecting X to transport, let's say prime. Although this is the same definition as given in the lecture notes, and I'll stop doing these prime versions in a second. Of now, there is actually a difference between this version of transport and the version in the notes. The version in the notes uses an equality between types, and that might have been what prompted the question instead of a line of types, a path of types. And that does actually change some things. So this is going to be a bit different from the version of transport that we see in the notes, which uses an equality, as you can see. But anyway, instead of dealing with equalities, if I just do these primed path versions, then that lets me not A to expand. From transport A of X. So I want a filler. Of course, because I put all of this text here. Now, what I can do is I can have a picture for this. So let's consider how I get to a point in A of I, right? Because at some intermediate point, I want to take X and I want to transport it to A of I, which is halfway across. So what I can do is I can write transp. And then I can do the family GLI to A of I. Let's say I actually put a parameter I here and make this J. So I'm going to go up to J, but I want it to stop at I. So I'm going to take the min operation. Let's see what happens if I take the min operation and then the max operation. So if I take the min operation, it takes me A of I to A of I1. And if I take the max operation, it takes me A of I naught to A of I. So I do want the max operation. This is the max operation. Sorry, this is the min operation. Yes, I'm taking the min operation. So in other words, and that makes sense because I want I to be a threshold. I want I to not be exceeded. So I take the min of I, and that's only relevant if j exceeds I. And if j exceeds I, then it doesn't stop succeeding at I, it just stops at I. So I want to take the mid operation. Now, since this is a transp, I can say where this is constant. And I want it to be constant when I is I naught. So in other words, when tilde I is I1. And then what I'm going to transport is I'm going to transport x, and this gives me a point at a of I. Now, so let's see, if I definitionally have I naughts, and I put I naught here, and I normalize it, I get x. And if I put I1 here, and I normalize it, then I get transp, and I get I naught here. So this is exactly a path connecting these two objects. Okay, so these were the primed versions, and that was a review. And now we're going to get into the exercises. But you can see that the role that this parameter of varph plays in the definition of this primitive transp operation, right? Any questions? Okay, so let's start off with JREFL, the computation law for J. Now, we're given basically a family that's parameterized by a base path space. So we're going to keep x fixed, and then for any other endpoint z and a path from x to z, we have type. Sure. So what is J? J is path induction. And then, as I'm saying, the motive of the path induction is it's something that's parameterized by the path space. So if you start off with x and then you go in an equality somewhere else, then for every single such path starting at x and going to any point z, we're going to define a type family over that data. Then what I'm saying is, in order to define a function on this base path space, well, the base path space is contractible. So it just suffices to give a single piece of data saying where the reflexivity path goes. And how we accomplish that is with J. So let's just look at what the definition of J is. And it just uses this subst operation. But it also uses the singleton contraction thing, which I don't exactly want to review. But the point is that if you basically have something which has a free endpoint, in non-cubical Agda, you'd say CC and you pattern match this to being REFL, and then you define it for the REFL case. Well, this is the REFL case that you give in the definition. And what it gives as a consequence is some term J, and where is J going to live? So what J produces, it's for every Y and P, it produces a point in the type PYP. So just given the value of this function on the base path space at reflexivity, you get the value of this function at the base path space at any point. And this is a non-trivial statement because you can't just make it constant because the family P is in general going to be dependent. So if we just look at this goal showing that it propositionally computes on reflexivity, you can see that this is a constant family, right? This is reflexivity, and I isn't involved in here. So this is just a constant transport. So all this says is that this is a constant transport. So transbrefl should work. And then all that I need to give is some term d. And that proves that the constant transport of d is d. And that handles this. Because that's all that the propositional computation law for J reduces to. Any questions? Was the explanation for J satisfactory, or did you want me to go over the implementation of J as well? Which I don't think I want to do time-wise because I want to get through some exercises. Okay. I've gotten an okay to move on. So for the next exercise, we're going to do something interesting. If we have dependent paths, then we previously, when dependent paths were first introduced, one of the notions that we had for a dependent path was that sort of transport provides a way here. So the idea is, suppose that you have some, let's say, line. Let's say this is your type A. And you have 2 points in it, X and Y. And you have a path between them. And there's a type family living over A. Let's call this B of A. And you can sort of think of it as a bunch of fibers living over it, but we're also going to just draw it as a blob. But the point is that if I draw a point here, then it's going to live over X. So let's say I have some lift of X to B of X, X prime. Then the question is, well, suppose that I have another point Y prime here. Then what should it mean to give a dependent path from X prime to Y prime living over this path downstairs, P? Well, the answer was that sort of you can take X to the fiber over Y using transport. So that gives another point, and that point is or rather, let's write it in terms of subst. Subst in B over the path P of X prime. And we said that there's a transport filling operation. So we get sort of a lift of this path from here to here. And then the new information that you have is this path here connecting subst BPX to Y prime. Subst is what we were previously calling transport in the non-cubical version of type theory. And the reason that this was a sensible thing was because we had a characterization of what paths were in sigma types. Now, the question is, can we go back between these two things? Because in cubical, we have a different notion of what a dependent path is. Because a path is just a map from an interval. I mean, up to some shenanigans about having endpoints fixed. We can just give a map from the interval, which at every point lives in B of P of I, right? And so that's our definition of what a path P is. And so is there a way to go from a path P to sort of these red fillers here? And the next two exercises define functions that go in both directions. So the first one is from path P. Given a dependent path, we want sort of the red filler from the transport in over A of I from X to Y. And the idea behind this is going to be a bit clever. What we're going to do is we want at every point, just a point in A of I1, right? Now, the question is basically, how do I get points in A of I1? Well, one of the ways that I get a point in A of I1 is just by transporting X all the way over here, right? But here's the idea. Suppose that we have sort of our path P, which we're going to denote like this. This is P. This is the value of I naught. This is a lowercase p. It looks like an uppercase p. So where this lives is rather, this lives in A of I naught. This lives in A of I1. And here we have P of I, let's say, living in A of I. Now, what we started off with was taking this point here, which was X prime, and we started taking X prime and transporting it to A of I. Well, how can I connect transporting X prime all the way here to doing just something that connects you to Y, right? So if I have P of I, remember that P of I is a dependent path. So for example, P of I1, P of I naught is definitionally X prime. P of I1 is definitionally Y prime in the notation of this. And we want a path connecting the transport of X prime all the way here to just Y prime. Now, what we can do instead is we can take an intermediate point, and we're going to move this intermediate point from X prime to Y prime. And that intermediate point is going to be P of I. So we want to take P of I, and we want to transport it over to the fiber at A of I1, right? So I need to write a clever way to write that transport down. So what I can do is I can trans. And now what I'm going to do is I'm going to consider the path GLJ2. Now I want this path to start at I. So I want to put a minimum operation, to ensure that the value of this path is no less than I. So now I put a min operation, not a max operation, and then I put J. Oh, sorry, A. So you can see that I'm going to put a var-phi arguments in here. And what var-phi arguments am I going to put? Well, when I is equal to I1, then I want this transport to just compute away to Y. So when I is I1, good things should happen. And if I sort of put I1 here, then you can see that it's a constant transport. So that's good, because in order to put var-phi here, we need when var-phi is equal to 1, we need this path to be constant on A, which it makes sense. So I can put I here. And the point that I'm transporting is something living in A of I. So I can put P of I here. So that gives me a point. Now, if I look basically at what happens when I normalize it at I naughts everywhere. Well, this is I naught, so this is just the regular transport. And this is going to be transport in the family A of the point X, which is what P of I naught definitionally is. And if I put I1 everywhere here, and I normalize, then I just get Y, because this parameter allows this to compute. So that's exactly what I want. And that fills the hole. Any questions?
How did you know that you wanted to connect this intermediate I to the I1 endpoint instead of the I0 endpoint?
Instead of the I0 endpoint. So I need to start off with this expression right here, this transport. And I want to generalize it to something that will allow me to go between this just transport and Y, right? Now, if you're thinking about what I'm doing, this is already happening in the fiber A of I1, right? This is an equality in A of I1. So if I'm going to transport P of I somewhere, it better be to the fiber of A of I1, because I want all of the actions to live in A of I1. Now, as for basically, instead of transporting X to Y, you can think of transporting P of I to Y. And then as P of I goes from X to Y, you're eventually just going to be transporting Y over the reflexivity path, because there's no more movement to go. But then this parameter comes in, and then that makes it definitionally computes to Y. Does that make sense?
Yeah, that was helpful. Thanks.
Good. Okay, now we're going to do the reverse, and the reverse is going to be pretty interesting. So now we want to go from a path P, from a transport to a path P. Now, the way that HComp works is that it's homogeneous composition. So homogeneous composition means that the type is not allowed to change when you write an HComp expression. In particular, this means sort of if you have a space X, right? You can imagine sort of, you have some expression on which you're doing HComp. This expression might be parameterized by an interval variable. So maybe you have something like this. Well, if you're going to stick in paths and try and do an HComp, which is to fill in this lid, then these paths have to live in a constant type. These are paths, not path P. However, this restriction of living in a single type is restricted to each vertical fiber. So in other words, I can have this point live in a different place than this point and this point, right? So the transport is homogeneous in that the type has to be constant only along each vertical fiber. And so what we have then is we're starting off with a non-dependent path. And a non-dependent path is happening entirely inside of the fiber A of I1, right? So we have here, for example, the points transport A of X, right? And here we have Y. And we have a path connecting them. That's given to us, right? So the idea from this picture basically was that if we wanted to get a path that connected X prime to Y prime all the way, all that we did is we joined together this path connecting this to this, the transport filler to Y prime, right? That was the entire idea. So we want to do a composition. How do we do a composition of paths? Well, in class, we learned that we could do it with HComp if we sort of put the reflexivity path here. And if we put this path P here, then this point right here is going to be X. So the question is, well, how do I connect X to transport AX? Well, we have an operation for that. That was a transfiller operation, right? That I went over. So if we just put that here, the point X is here because this is just a constant path. And then where is this going to live? Because it's homogeneous composition. If I is a certain value and you consider that HComp expression, it doesn't change the type. So at I, this fiber everywhere is going to be in A of I, and so is this top point right here. So in other words, the lids that we get for the box is going to be a dependent path over A as we want, because the composition operation is homogeneous, but only on vertical fibers, which is good. So then I guess I'll delete this and I'll just write the HComp expression from scratch. We're going to do HComp, and this takes two arguments. It takes the filler at the bottom. Well, I guess I put an I here, but that's fine. Now, I sort of don't know what I want to put in the bottom. So here I'll just do lambda, and then I'll do a pattern match lambda with two arguments. The first is going to be j, because I need to give a new path. So I'm introducing a new interval variable. And I'm going to consider the case when I is I naught. And then I'm going to consider the case when I is I1. So when I is I naught, I just want the constant path. So I'll just put X here. When I is I1, I want a path in the fiber at A of I, which is going to be this path here. That's the action happening in the fiber A of I naught, sorry, A of I naught. So I'm going to put P of J. J is this interval parameter here. I is a definition of the I1 in this expression. And at the bottom, I want to do a transport fill operation. So we covered it here, and it's in the notes as well. So transport fill, I'm going to then give sort of, let's see what I need to give. I need to give an equality from A to B. Well, this is given as I to type L, so I'm going to need to A to expand that in order to convert an equality, a line into an equality. And that's an unfortunate thing. Sometimes you have to do this eta expansion. It's not a redundant eta expansion, it's a necessary one. Then I'm going to need to give a point A of I naught. Well, that's my point X. And this gives me a connecting path. And I'm going to evaluate, I guess maybe I should call this parameter J, because it's different from the I from before. I'm going to evaluate that at I. And that gives me a point in A of I, right? And those holes fill. So from the picture before, we saw how we thought about this, right? Composition is homogeneous. So basically, if I sort of consider this expression at a specific value of I, well, this stuff is only going to be relevant when I is a specific thing, right? So if I is I naught, this is going to live in the fiber A of I naught. And this transport fill operation, if I put I naught here, it's going to just definitionally be X, right? So at I naught, this all lives in the fiber A of I naught. At I, that's not I or I naughts, well, this boundary data is not relevant and this lives in A of I. So the H comp expression as a whole is also going to live in A of I. And at I1, this expression is relevant. And again, this entire expression when I is I1 lives in A of, so I guess I can make this into a whole. And I can do something like consider putting in a specific value for I. So let's say I put I naughts. Well, then you can see, oh, sorry. This is in the context of I is something. I sort of can't specialize I to be something because it's used in this partial operation. So that demo doesn't work. But hopefully the explanation that I give suffice. Do you have any questions? Okay, so here's a really cool application of the thing that we just proved. Suppose that you have a proposition. Well, what does a proposition say? A proposition says that any 2 points in the proposition have a path connecting them, right? But what if I have a line of propositions? Can I find a dependent path connecting any 2 points living in different fibers? And the answer is yes. But how do I prove that? Well, I want to produce a path P, right? So how do I produce a path P? Well, what I can do is I can start off with a dependent path. So what I can do is I can transport A of I naughts. Transport, let's say in the family A. That's going to be a relevant argument. Transport in the family A, the point A naughts. And A needs to be an equality. Right? Now, I have a proof that every single fiber is a proposition. So what I can do is I can take P. And then what do I need to give? I needs to say, well, at what point am I going to consider? I'm going to consider the point I1. And then I get is prop AI1. And then I can provide 2 points in AI1. Well, one of them is going to be this transport. And the other one is going to be A1. So that I get a path from the transport of A naughts to A1. But then I can apply this 2-path P operation onto this. And if I try and infer what the type is, well, it's not going to know. But from the ambient context, it is going to be able to infer what A is. And that hole is going to fill. So that's cool. That's a pretty useful thing. And this is called is prop path P. The much more useful lemma is sets to square P, which is the analogous statement for sets and filling in the boundary of a cube. So the reason how you think of this is basically you have a line of types and you fill in the endpoints. And then if you fill in the endpoints of a one-dimensional cube, you get a filler inside of the cube. One dimension up, it's if you fill in the boundary of a two-dimensional cube, then you get a filler of the inside of the cube. And in general, every single point in this square is going to live over a different fiber. You'll get a square of types. Okay, let's look at the next proposition. So this is the idea of a subtype. What is a subtype? Let's say you have a type and you form a sigma type, where the second component of the sigma type always lives in propositions. So classically, which is not how we're working, we think of a proposition as either being true or false. So basically, this cuts down on the type for all of the elements which are false and throws them away. But that's not how we're thinking about it. That's a very classical way to say it. So we start off with the data of a type family over its two elements in the sigma type, and a proof that for every point, the type family is a proposition. And we have an equality between the first components of the pair. Well, the catch is if we have an equality between the first components, then we sort of know that the proposition over the first components is true in both cases. And it shouldn't have any other information, right? So if that's true, then it should be true that U and V are equal. So in a sigma type where the second component is a proposition, providing an equality between two elements, it suffices to provide equality between the first components. So let's see how we do this. Well, we want to create a path between them. And it's great. We're working in dependent type theory. So let's just make it an interval variable. Now we want to connect a path between U and V. And remember that in sigma types, we have definitional eta expansion. So we can sort of write, well, we have a path between their first components. So I can say P of I is the first component of the path and then something. And if I look at the deduced type, it's just going to tell me it's in B of I, and it's not going to give me the constraints. The constraints are going to be displayed here, and that's a bit less useful. Okay, but let's think about it. So where this lives is in B of P of I. So I have a proof that B is true of the first components, and that B is true of the first component of U. You know what? Maybe I can pattern match. Let's say that U is X naught y, and that V is X1 Y1. I'm allowed to do that. Then you can see that I'm connecting these 2 points. And then you can see that P of I and V does connect the first components. Now, okay. Now I want to create sort of a path between the second components, right? So if I know that a proposition is true, then I know that every single other proposition in a path over it is true because I can just transport X all the way over to any other fiber, right? But the catch is that when I get to the end of it, I'm going to need to do something, right? When I get to the end of it, I'm going to have the transported operation. So this makes me think that I actually don't want to put the interval variable here. Instead, what I'm going to do is, well, maybe I can write it as an equational reasoning. So I'm going to start off with, I guess, the pair X naught Y naught. And then I'm going to consider the path GLI to P of I, comma, and then I'm going to consider transporting, or let's say transfill. Transport fill. That takes a parameter D. And then I'm going to consider doing that with respect to the point X naught, or rather Y naught. And then I'm going to evaluate this at I. Oh, it expects an equality. B of P of I. Okay, let's look at the type of transport bill. So oh, sorry. This is a point, of course. This is a point, it takes a point in A. It's not a path. So I want P of J. Or in other words, I can write this in a different way. If I have my path P, that's an equality between the two of these. So I can write app B of P, right? That's another way to write it. Yeah, perfect. Now I'm going to take the point, why not? And then I'm going to get a path here. But if I evaluate it at I, then I get something that exactly lives in here. And so that should be happy. Except for the fact that it's not happy. Oh, because, of course. Okay, so let's see sort of CS. If I fill this in, I get P of I1, and P of I1 is definitionally going to be Y1. Sorry, X1. And this is going to definitionally be something else as well. If I just sort of normalize this, then it's just transport. On app P of I of Y0. Right. And apparently these parentheses are necessary. Now what I have is that I have a proposition. So I want to show that this is equal to X1, Y1, right? So how do I connect these two components? Well, on the first component, I don't have to do anything. And on the second component, I have a proof that something is a proposition. So what I'm going to do is I'm going to take H. I'm going to evaluate it at the point P of I1, which is Y1. Or rather, X1. And then I'm going to give 2 points. One of them is going to be this. And the other point is going to be Y1. And that gives me that equality. So bam. The idea is first we did a dependent path to connect this to the transport. And then from the transport, we use the fact that it's a proposition to connect the second components entirely in the fiber B of Y1, B of X1 rather. Then we use that it's a proposition. Okay, so I have 15 minutes and I have the one hard exercise left. Are there any questions, by the way? Okay, sorry, I want to go exercises 8, then I want to go solutions 8, and here I want active information. Okay, good, we're good. Oh, and then I see there's a suggested solution. Two path P. Oh, that's a great suggestion. Yes, I unfolded the definition of two path P. Basically, that is something that happens. Except instead of doing an H comp, I did it in 2 steps. So your suggestion is beautiful, and I will use that suggestion. We basically have that exact same idea as before. This idea that I described, I'm like, why is this so familiar? And it's because it's the idea that I was describing for the motivation behind two path P. So another thing that we can do is we basically have sort of this path right here that we constructed, right? And that's a path from transport. So I can instead do two path P of that expression right here. And then I can put an I here. And then I can put a P of I here. And then I can put a I here. And there is an unsolved meta. Sure. Really, there's an unsolved meta. Fine. Did your solution also give you an unsolved meta? If I use the sigma path P lemma. Oh, I see. Okay, I see. That is why I imported a solution 7. Okay, that makes sense. I could also reuse is prof to path P. That's another suggestion. Okay, so this is a thing that works, and I can get rid of the meta by specifying it or by using it in another lemma. But also I have this is prop to path P lemma, and that's actually a great idea. I really like that idea. So basically we're going to sort of take a path. Well, that path is going to be H GLI to H of P of I, right? And then I'm going to give Y naughts, and then I'm going to give Y 1. And then I get a path P for Y naught to Y1. And look, a no metas, that type is already filled in. So what I do is then I put a I here. And that works as well. So all of these solutions work. I actually like the third solution best. That's the most elegant solution of the bench. Okay, and now I'm fine going a bit over time. This exercise, I wrote the problem set, but I left this exercise to do on the fly. So I saw the solution that I'm like, okay, I'm not going to fully observe the solution. I want to figure it out as I go. So we want to show that being contractible is a proposition. What that means is that basically, given any 2 points that are centers of contraction, and then if we sort of look at what the types are, H is for every other point a path connecting C1 to Y or C0 to Y, right? Then what I can do is I can say, well, okay, sure. How do I connect C0 to C1? Well, I could do something like H1 of C0. Or H0 of C1. And then I need to fill in the second component with something else. Let's make this an I knowledge chain. And now we're going to need to be clever. So I want a path, a point in this path type. Well, to give a point in this path type, I can sort of abstract over it. And then what I need to do is I need a path from H naught of C1 of I to Y. Well, at this point, maybe I can also abstract over J. And what I see is that it's not being very compatible, but I can sort of draw this cube out. Because they sort of have the boundary in a less useful way at the bottom. So you can see that that hole at J is equal to I1. So let's say this is my I axis, and this is my J axis. So when J is equal to I1, so this is my J axis. When J is equal to I1, I want it to constantly be Y. When J is I naught, I want it to be H naught C1 of I. And if I consider the expression H1 C naught, that's a path connecting C naught to C1. So I can put C naught here. And then I can put C1 here. And this path at the bottom should be H naught of C1. Right? Now, what do I want at the sides? When I is I naught, I want the path H naught Y of J. And that connects C naughts to Y. This connects C naughts to C1. And this path at the top is reflexivity. Now, this isn't a literate Agda file, so I should make this into a comments. And what do I have at this side? Well, at this side, when I is equal to I1, I want H1 of Yj. Of Y. Okay, so I want to fill in this square right here. And the question is, so how do I fill in a square like that? Well, what I'm going to do is I'm going to start off with a square that I can fill in. And then I'm going to fill in this other square here. So I'm going to do an H comp. And what I want basically is I want a filler of a square. So how I get a filler of a square is I'm going to H comp from a filled in square at the bottom that I'm just going to get from stuff. And sort of what sort of filled in square can I really do? Well, I guess there are several choices. So this is going to be the top. And then I'm going to have a bottom. And what I can do is, well, I can say, let's say, maybe there are lots of choices. Okay, so this is something that I'm able to do. And then the question is, am I going to have a way to sort of fill in the sides to connect these two things? And the answer is should be yes. So how do I parameterize the square at the bottom? Well, first off, so I'm going to do an H comp. Then I may as well abstract, and I'm going to do K. I is equal to I naughts. K I is equal to I1. J is equal to J naught. J is equal to I naught rather. Okay, and at the bottom, I could basically fill in whatever square I want. So what I'm going to do is I'm going to consider evaluating, well, basically, how do I sort of get this type? I sort of want this to be constant on the diagonals. So when when one of them is 0, I want the full expression to be 0, and only when both of them are 1. So I'm going to take the minimum of it. So I'm going to take H naught of, and this is going to be an expression in I and J, I min, so wedge. Sorry, H naught of C1. Okay, great. Now I need to fill these things in. So connecting this to this is easy because they're the same. So when J is I naughts, I just want the expression H naught of C1 of I. H naught of C1 of I. Oh, I want to take this takes, okay. So what happens if I take wedge? Well, if I take wedge, because yeah, I do want wedge. Sorry, I want V. The max, because if I'm here, then one of them is 0, but I want it to be at 1. You're right. Okay, so then everywhere here, it's just determined by what this is. So when J is I naught, this following expression should work. And it does fill. And so that's good.
Oh, what just happened there? Could you walk through why and was incorrect, but or is correct a little slower, maybe?
Yes. So basically we want this to sort of be constant on maps that look like this, right? And then sort of we can imagine sort of this filler here, right? So for example, except for the fact that sort of this really should be the same number of squares. This should connect us all the way to okay, like that, sort of. It's not an equal number of spaces, but you get the idea, right? In terms of sort of, I want sort of these to be the lines at which the function is constant, right? So if I and J is anywhere along this line, then it should have the value H naught of C1 of I1, right? And then everywhere here, it should have the value H naught C naught of I1. Well, so for example, if I is equal to 0, then how far you are along is determined entirely by J. So I shouldn't matter at all. So if I is I naught, then for the max operation, I is involutive, right? Whereas for the OR operation, it would just constantly be I naught here. And then this side wouldn't work because this side would just be a constant, right? At C naught. It wouldn't go to C1, but we want this boundary. So OR is the right operation. Max is the right operation to take.
That last bit didn't make a whole lot of sense to me. It looks like the diagonals that you're trying to draw. For a moment, I thought maybe you were trying to say something about those being like the lines of like constant lines in some formula, but the constant lines in
So
the
for
formula
every
for both.
2 points, I and J, you get a value of this expression, right?
Yeah.
So along this line, that value is constant.
That's not true.
Yes, it is. Because sort of you can. Oh, you're right. It's not true. You're right. Okay. However, it's not true because sort of the lines are sort of bent out. Okay. Fine. I did lie. Because here it would be halfway true. Okay, my explanation does not work. But the point is that if you look at what it is along these boundaries, it works out, right? For example, along this boundary, if one of them is I naught, then the other one determines the value, right? So traces this path. Do you agree with that?
If one of them is I naught, then the other one traces that
out
path.
this path.
Okay, sure.
Okay, now imagine that one of them is I1. Then this entire expression, you have a max with I1, so it's just going to be constant at C1, right?
Uh-huh.
So in other words, this is a filler of the requisite square. We sort of don't care what the values are in the middle. The boundary is this specified value at the bottom, right? So along this path, the expression I or J is equal to just I. Along here, it's just J. And here it's I1, and here it's I1, right?
Uh-huh. And so so you're saying because the two edges that are ruffles, you just want an expression that takes some constant value on the ruffle edges, and you care less about what happens on the other two edges?
Exactly.
Gotcha. Okay.
So basically, I'm able to fill this square. This is filled. Right? So we don't have to care about it. But the point is that I can basically transform this boundary into this boundary uniformly. And then the HComp operation gives me a filler here, which is what I want. So for this bottom edge, I got the side because it's just the same thing as I want here, right? Now, let's think about sort of this top side. We want to connect C1 to ruffle. So this is the J is equal to I1 operation. Well, what we can do is we can take so do we take H naught or do we take H1? Well, rather, let's think about sort of this side here. Let's consider the I is equal to I naught side. We want to connect this to this at every single point J. And what we can do is we can use the H1 operation. So H1, oh, it's not so easy. Or rather, what we can do is we can take H naughts and we can change what the argument is in here. So we're going to consider H naughts of something that connects C1 to Y. What connects C1 to Y? H1 of Y connects C1 to Y, right? So if we sort of imagine changing this as k goes from 0 to 1, then if we take h naught of this and evaluate that at j, then let's see what it is when k is I naught. When k is I naught, we get h naught of c1 of j, right? When k is I1, we get h naught of y of j. So this is the appropriate filler for this side, right? You sort of are changing this c1 into a y. That's what you're doing as you go upwards, right? Now, let's just consider what that expression is right here at sort of this boundary point here. Because that suggests what the top filler should be. So when j is I1, this normalizes to h1 of y, k. So h1 is the path being traced from here. Oh, thanks. Yeah, yeah, okay. Great. So I will post that in a second. Yeah, so there's a constant width font. So here, we found that the path being traced at this corner when we fill that square is h1. So what we're going to do is we're going to do the h1 path here. Rather, this is the j, this is j is equal to I1. So we want to trace the path h1. And we want to connect c1 to y. So h1 of y of k. And that fills. And so we have one more side to fill. And it has some specified boundary. And what we're connecting is REFL to h1 of y. So if we sort of think about it, this path right here and this path right here, they're sort of hard constraints. We want this goal when so at the bottom, it should just be reflexivity. And on the sides, it should be two different things. So let's figure out what the sides are. So the last filler. This is the last thing in our way. So what do we want to fill? Well, at the bottom, we have reflexivity, right? At C1 to C1. Let's see what we have at the left side. So at the left side, we are going to consider this expression here, which is the j is equal to I naught expression. And we're going to consider that expression when I is equal to I1. So that's just a constant path at C1. Now, what about the other side? So we want to connect it to h1y eventually. For the other side, we're going to consider the j equals this expression. And the catch is sort of there's no dependence already. So it's going to be h1 of, or rather, sorry, yeah, h1 of y is going to be this path. And that connects C1 to Y. And the path that I want at the top is going to be H1 of Y, right? But that looks like one of these sort of connections. So we just need to do a bit of cube magic, right? So this is sort of great. We're in a great position. So this is sort of the last filler. How do I fill this? Well, I'm going to consider the expression h1 of y. And then I'm going to evaluate it at some expression of k and j, right? Now, sort of that time we used the connection where we used the max operation, and that sort of filled that. This can also get filled. And it looks like we should just use the opposite thing, the min operation. Or rather, wedge. And it fills. So basically, it would be a bit easier to do on paper because it's a bit easier than doing ASCII cubes. But look, we were able to figure out what this was, right? So we started off basically, we want this specified boundary, right? So what can we do? Well, we can sort of fill in things when there are these degenerate connections, right? And then the question is, how do I do each side? And the side that was tricky was this side. That's the side where we really had to think. And for that, we just drew out what the required thing was, and we saw that it was another one of these connections. And so that accomplishes it. Now, Lambda Duck posted a cube in the chat. I will paste that cube, and I will try and make it aligned. Oh, look, it's already monospaced. Wait, but this doesn't look like a cube exactly. Oh, sorry, this is a diagram of what the isotropy lines look like. Yes, the isotropy lines aren't diagonals, they're lines like this. So sort of, I can consider these the isotropy lines of a connection. I understand what this diagram is. Okay, that was really cool. I really enjoyed this exercise session. So especially this problem. I deliberately left it's for me to figure out live, and I'm happy about that choice. It ended up paying off. Why were the 5 new squares easier than the original new square? Well, the problem is that basically, it's what are our starting points? Our starting points are really these connections. If we want to fill in a square, then one of the easy ways that we can fill it in is if we have connections, right? So if I just given a boundary, I can't just magically fill it in. I have to start with something known, and then I have to modify the known thing by making sides, right? Oh, yeah, and there was a solution that was posted on the Discord from the TAs. And I think the solution might be a slightly alternative solution, or it might just be the solution that we consider. You can see that there are 2 connections there, but they look like the same connection. So maybe the person who I think was RTM teaching that, he started off with a different connection than the one that I started off with, and then you get a slightly different thing. But I chose to start off with, sorry, let me screen share that as well. So this might have been done live in the tutorial, but as you can see that there are 2 faces which are connections. Oh, the face that got started off with was just a constant face. That's interesting. So if you start off with the constant face, then that's possible as well. But I chose to start off with this connection. Okay, so starting off with the constant face is also an idea. But anyway, that was cool. So we filled in our first actual cube, actual like 3-dimensional cube. And I went a bit over time. So I think I'm going to stop the recording now. Thanks everyone for joining.